Hey guys, this video is intended to be an introduction to work and energy. Um, Looking at the quick objectives here, we're going to talk about kinetic and potential energy. So just a quick review of the types, and then we're going to relate this to how this relates to the physics definition of what work is, and talk about that. And then we'll do a few examples, calculations. So I'm sure you'll remember from last year or years prior, two basic types of energy, potential energy and kinetic energy. Potential being stored energy within an object, and kinetic has to do with the motion of an object. So I'm assuming you are already familiar with these. Specifically, we're going to be talking about a specific type of potential energy called gravitational potential energy, and it has to deal with energy stored, because there's gravity on Earth. Like when you lift something up, there is potential for it to fall back down. It has gravitational potential because gravity can pull it back down. So we'll be talking about gravitational potential. I have a really bad stylus here. Gravitational potential. Again, there are other forms of potential, but that's just one that we're going to be discussing a lot. And kinetic energy is energy with motion. Basically, if something is moving, it has kinetic energy. You all know the basic definition. We're going to be using this at least once later on, so I'll go ahead and give this right now. To calculate the kinetic energy of an object, it is related to its mass. The heavier it is, the more energy it has, and its velocity. So the K represents kinetic energy, of course. The unit is the joule. So joules is the unit. This is abbreviated with just a J. The mass obviously is in kilograms, and the velocity is in meters per second. So that's just, really there's no other way, or I'm sure there's other ways, but you know what it is already. Here's how to calculate it, and we'll be using that a little bit later. So let's look at what is work, the physics definition. I thought we can start off with a few examples. Are we doing work or are we not, and discuss, kind of develop the definition from there. So I'm looking at this first one, a weightlifter lifting a barbell. I invite you all to read through these real quick. If you want to take a guess on your own, you can pause the video or whatnot. But a weightlifter lifting a barbell, is this work? And you may be thinking, well, it would sure seem like the weightlifter would have to do a lot of work to lift this, depending if it's a really heavy barbell or whatever. Indeed, this is an example of work. All right, the biggest thing to ask yourself when is work being done is the energy of the object changing. Anytime that you are doing work, you are changing the energy somehow. And also another way to kind of check is, are you applying a force? If you apply a force and as a result that object then moves, then you have given that object kinetic energy, for example. Thus you have done work, right? You have given it energy, you have applied a force. That is work. So similarly in the second one, pushing a crate up a ramp into the back of a truck, again you are applying a force on this crate. It is moving, is raising into the back of a truck, so this is also an example of work. Notice in these two, what type of energy have we changed? We have changed its potential energy, right? When the barbell goes from the floor to above the weightlifter's head, it is now higher than what it was. It has more gravitational potential energy. Or while it was moving, before it was at rest on the floor, then the weightlifter lifted it, or you pushed the crate, and while you're pushing it or lifting it, it's moving, so it has energy. That's another way to think about it. This third one here, pushing against a heavy truck in an attempt to move it. So we are definitely applying a force to this truck, right? Let's say it's a semi-truck. You can't move it in an attempt to move it. So are we changing the energy of this truck? And the answer is no. We are not. There is no work being done. It may seem like you are working very hard to push it, but you are not actually giving it any kinetic energy, any potential energy. It's not moving. There's no work. Sad day. Wasted. Yes, I guess you can say your muscles are using energy and you're losing energy in that respect, but you are not doing any work on this truck. I'm thinking really hard about a math problem. I kind of put this in here to contrast. Obviously, this is not an example of work. Contrasting how we use the word work, homework, I'm going to work in everyday life, and how it is different than what work in physics means. So I'm thinking hard about a math problem. Clearly, you are not changing the kinetic energy of math or whatever. So doing a push-up, we are applying a force on your body, right? Your body is moving upwards, so it is moving a certain distance. Yes, you are changing your energy. You're higher than when you were before, so you are doing work. Gravity pulling on you while you stand on the ground. No, not work. You're standing, you're not moving, your energy is not changing, you're just sitting there, right? Or standing there. So yes, gravity is a force, but it is not moving you. So not work. Friction slowing down a box after you slide it across the floor. So friction is slowing down the box. So is it changing the box's energy? And yes, it is, right? It is. Before the box was moving fast, then it was moving slower, so it has lost kinetic energy. And so this is an example of work. Friction is a force, and it is pushing on the force over the distance that it is applying. This last one is a little tricky. This is not an example of work. It may seem like it is, right? Gravity pulling on a satellite as it orbits the Earth. Yes, there is a force. Yes, the satellite is moving. So we're like, well, seems like there's work being done. But the key is that gravity is not causing the satellite to orbit the Earth. Gravity itself is not changing the satellite's orbit. All right, I mean, if it goes in a circle, it's not moving any closer to the Earth. Right? There's no distance there. It's not speeding up. Right? So there's a whole bunch of ways to think about it. And really, when it comes to this, we'll talk about on the next slide. But the force has to act in the same direction that it moves. So let's look at the now that we kind of looked at those examples, let's define work. Really, the most important thing to think about is this energy transfer, relating work to energy. Work is a change in energy due to you are transferring energy somehow, whether typically or almost always kinetic and potential energy, and that change occurs because you are applying a force. And again, the object has to move. So there's a few details there, but work is energy transfer. I kind of put a little checklist here. If these three things are met, then work is being done. If you are applying a force, the object is moving. That is implying that you are changing its energy somehow, because perhaps it wasn't moving before and now it is. Or perhaps you're fighting friction. You have to apply a force to fight friction, so it is moving. So you're working against friction. And this last one, the object moves in the linear direction of the force. So it's kind of relating that to the gravity one. Let's kind of draw a little diagram. If this is the Earth and this is the satellite at the top, gravity is pulling that satellite downwards, right? Towards the center of the Earth, it's pulling it down. But which way is the satellite going? The satellite is moving this way. Or let me draw a black arrow here. This way. And so it is not moving in the same direction that gravity is acting. I will say that the key thing is this linear direction. So take a quick look at the friction example. So let's say that's my friction diagram. There's the friction acting right there. If let's say the box is moving to the right, friction is going to slow it down. Friction is going to act to the left. That does not mean that it's not doing work. It is still moving in the same linear direction. It's just in the opposite direction, so it's actually slowing it down. But friction is doing work, even though it's not acting in the same direction that it's moving. It's in the same, I guess, line, on the same line, left-right line of it. So, there's the bell. Okay, so mathematically, how do we write this out? Work. So the first two criteria, force times distance. So F times D, work is force times distance. This is obviously work. The unit is also joules. It is, like I said, very closely related to energy. The F represents force in newtons. Force in newtons. And this D represents the distance that the object moves. That it moves, this is in meters. So the first two criteria, you're applying a force and it moves, are demonstrated in that very simple formula. You just multiply them together. Similarly, right, we also said that work is an energy transfer, right? That was in the definition. So similarly, we can say that that work is equal to the change in energy of an object. If you give it more, if you somehow give an object more energy, you are doing work on it. How much energy you give it is equal to the amount of work that you do. Equation form, this would just be delta, right? Change in energy. So it's similar to momentum, right? There is momentum, which was related to the mass and velocity of an object, and you had impulse, which was the change in momentum. This is very similar. You have work, and then you have energy, and you have change in energy. So, and you'll find as we continue the unit that energy and momentum are related in multiple ways. So let's take a look at a few quick examples. This is a very basic one. Josie is pushing a crate, mass 32 kilograms, across a floor or a room that's, I say, 13 meters. Well, I guess that's kind of a vague problem. Let's say she pushes it 13 meters to the end of this room. And so how much work does she do? She's applying a force. So the force is equal to 150 newtons. 50 newtons. So what do we got? Work is force times distance. So this is a very basic problem. Obviously the force that she's using is 150 newtons, and the distance is 13 meters. And so the work done, choose blue please, thank you. Work done is 1950, I believe, joules. Sorry. Not too bad. Another one, weightlifter lifts a barbell, mass equals 100 kilograms, and lifts it at a height of 2.5 meters. That's about the height above someone's head. How much work does the weightlifter do? So we have the weightlifter with the really long arms, lifting this barbell. The mass is 100 kilograms. And so this is before. What force does he have to apply to lift it? Right, remember this is just the mass. So if free body diagram real quick, what is the downward force is the weight, right, mg. So he has to apply a force equal to that in order to lift it. So remember g is equal to 9.8. And so the weight of that object is actually 980 newtons. He then lifts it to a height of 2.5 meters above his head. So the work force times distance. So the force that he is applying is 980 newtons. That is the weight of the object. And the distance that he is lifting it, that he's applying that force for, is 2.5 meters. Let me draw that down here. All right. And so the work that is done is what, 2.5 times 980, 2,450 joules. So let's think about this in terms of change in energy. How is the energy changed? What type of energy is different with this barbell? And if he's lifting it above his head, he is changing its potential energy, right? It's gravitational potential energy. And the barbell is higher than when it started, thus it has more energy. So he has changed the object's potential energy by amount of 2,450 joules. The last one, we have friend Josie again. So that she pushes, so this is that box that she pushed. Let's say she releases it, and then it slides across the floor, and friction stops it. So we've already talked about how friction is doing work when it slows something down, right? It is changing its energy. The initial speed of the box is 1.0 meters per second. So how much work is being done? So initially this box is moving with a speed of 1.0, and it has energy, right? It has a certain amount of kinetic energy. It is moving, and then it comes to rest. So then the velocity stops. So what mass is 32, that sort of thing, equals 32. So so how much work has she done? So obviously, from a problem-solving point of view, I didn't give you the force. So clearly, we're not going to be using the force to solve the problem. But we are relating this to its energy. Work is the change in the energy. So let's determine how much energy does it have. Initially, probably should change colors here. Kinetic energy, this should be just K, equals 1/2 mv squared. Let me change colors here. So this is 1/2 of the mass, which is 32 kilograms, times v squared, 1.0 meters per second squared. And so it starts off with kinetic energy of 16 joules. Similarly, at the end, kinetic energy is 1/2 mv squared. It's not moving, so there's really nothing that needs to be done. It ends with no kinetic energy. So what is the amount of work that is done by friction? Work equals, let's go to red here. So work equals change in energy, which is final minus initial, right? And so it ended at 0 joules, and it began with 16 joules. So the work that was done was negative 16 joules. Negative work, is that possible? It is. Think about it. If work is the change in energy, and this box has lost energy, it has slowed down, then it has done negative work. So friction is a very common example of negative work, because friction will always decrease the energy of or at least resist motion of an object that's moving against a surface. So the work can be negative. It can be positive if it's gaining energy. It can be negative if it's losing energy. So yeah, I'm done. See y'all guys in class.